Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 32, the JK FlipFlop of Chapter 6, Flip-Flops of the course Digital Logic Design or Digital Systems or Digital Electronics. This slide is a disclaimer for you to read. I cite 3 references, however, there are many books in digital logic design. Today we will talk about the JK FlipFlop. In the Chapter 6 contents, we covered sequential networks, memory elements, the SR flip-flop, and the clocked SR flip-flop. The JK flip-flop removes the ambiguity in the truth table of the SR flip-flop. If you remember when you covered the SR flip-flop, the last 2 lines in the truth table, the detailed truth table, they were not allowed because the inputs when S is equals to R is equals to 1 will cause Q is equal to Q prime, and this is against the definition of Boolean algebra and the definition of the flip-flop. Therefore, the JK flip-flop will remove this ambiguity and will solve this problem. The input J and K of the JK flip-flop, like the inputs S and R of the SR flip-flop, set and reset the flip-flops respectively. J will set the flip-flop and K will reset the flip-flop. However, there is no ambiguity that J and K, they can be equal to 1, and at that time a Q plus will be the complement the complement of the value of a Q. It means it will be a toggle mode. If a Q is 0, will toggle to 1. If Q is 1, will toggle to 0, as we will see it in the truth table of the JK flip-flop. So the combination J is equals to K is equals to 1 is allowed, and when it occurs, the flip-flop switches to its complement state known as the toggle state. That is, if Q0, it toggles to Q1 and vice versa. The figure shows the logic symbol of the JK flip-flop shown here in figure A. And show you the implementation of the JK flip-flop using SL latch or SL flip-flop. So the figure shows the logic symbol using SL latch and 2 AND gates. J and K prime are applied to one AND gate. The output S is equals to JQ prime, while K and Q are applied to the second AND gate with the output R is equals to KQ. So simple implementation for the JK flip-flop. This implementation will prevent S is equals to R is equals to 1, as we will see shortly. So if we look at the truth table of the flip-flop, there are 4 possible combinations for the excitation input J and K, and these are either 0, 0, 0, 1, 1, 0, and 1, 1. And the Q will be 0, 1, 0, 1, 0, 1, 0, 1, depends on the present state, which is the output of the flip-flop. Q prime always the complement of Q. Now, based on those 2 logic equations, we can evaluate S and R. S and R. So when S is equals to R is equals to 0, this is the hold mode, and Q plus will be equal to Q. See 0, 1, 0, 1, and here also it is 0, 0 for S and R. So 0 will stay 0. Well, when it is 0, 1, this is the reset mode. So we have 0, 1. The output, if Q is 1, the output will be 0. Okay, because it will reset mode. When S is 1, so this is the set mode. So if Q is 0, this will be 1. So this is the set mode. 0, 0 is the hold mode. So 1, okay, is going to stay 1. And 1, 0 is the set mode. So 0 will become 1. And 0, 1 for the SR, okay, this is the reset mode. So 1 will become 0. So we evaluated the truth table based on the SR values from the truth table of the SR flip-flop. S and R were evaluated from the 2 logic functions, which is simply S is equal to J Q prime and R is K Q. Those simple equations. So in the truth table, but really, if you look at JK, when it is both zeros, this is the hold state, you will get 0, 1. Forget about SR now. And when it is 0, 1, this will be 0, 0, which is the reset mode. And Q plus will be 0 all the time when it is 0 and 1, when J is 0 and K is 1. And when J is 1 and K is 0, this is the set mode because we get 1, 1. Okay, and this is the set mode. But when we have 1, 1, whether it is 0, when Q is 0, we'll toggle to 1, and when Q is 1, we'll toggle to 0. Call it the toggle mode. So the toggle mode Q plus will be equals to Q prime. So in the compact truth table, JK00 Q, which is the hold mode, 01 will give me 0, which is the reset mode, 10 will give me 1, which is the set mode, and when 11, the Q prime or the toggle mode. So if the Q is 0, it will toggle to 1. If the Q is 1, it will toggle to 0. So very interesting that the JK flip-flop, it is a special case of the SR flip-flop. We proved the truth table based on the SR latch, and it works fine. So it is really simple, easy by looking at the SR values, and the SR values again were derived from the logic equations, and those logic equations came from the hardware circuitry. So R is equal again to KQ, and S is equal to JQ prime. Now this circuit may exhibit a race round difficulty, and we remove this difficulty with another circuit. We'll show you this circuit shortly. Now from this detailed truth table, we can draw a K-map in terms of JKQ as inputs, and the K-map for the Q plus, and we get this Q map, so we can derive the characteristic equation of the JK flip-flop. On the truth table, Q plus will be 0, 1, 0, 0, 1, 1, 0. For the Q plus will be JQ prime or K prime Q. So this is the characteristic equation of the JK flip-flop. This equation describes the behavior of the JK flip-flop. So from the truth table, we can get the characteristic equation, or from the characteristic equation, we can get the truth table. The excitation requirement, we look at the transition between Q to Q plus. What's the value of J and K? We did this with the SR latch on flip-flop. It's the same thing. For the transition from 0 to 0, we need J must be 0, but K don't care. We don't care. K could be 0 or 1. This is what the don't care means. So the transition from 0 to 0 will get J must be 0 and K is don't care. And this came from here. See, the transition 0 to 0 will occur in the first row, 0 to 0. And it will occur in the third row, 0 to 0. In the first row, J is 0 and K is 0. In the third row, J is 0 and K is 1. So K could be 0 or 1 or don't care. The same thing with Q 0 to 1 will be 1 don't care. 1 to 0 will be don't care 1. And 1 to 1 will be don't care 0. Once we have the excitation requirements table, we can have the state graph of flip-flop. We have two stable states, 0 and 1. And if I'm in state 0 and I transition to 0, I'll remain in 0, 0 to 0. I need 0 don't care. See, we write on the row 0 don't care for the value of JK. If from 0 to 1, if I go to state 1, it will be 1 don't care, 1 don't care. So 0 to 1 will be 1 don't care. From 1 to 0, it will be don't care 1. It will be don't care 1. 1 to 0, it will be don't care 1. And if I stay in state 1, from 1 to 1, I would need don't care 0. So I stay in state 1, J will be don't care, and K is 0. So this will be the state graph of the JK flip-flop. So we got everything we need. We understood the principle of the JK flip-flop using SL flip-flop. We derived the truth table, the detailed and the compact truth table, and we derived the characteristic equation, and we derived also the excitation requirement table and the state graph of the JK flip-flop. And now the master-slave JK flip-flop is very stable, and it's very useful circuit, and the stability of this JK flip-flop make it really superior over the SL flip-flop. A more practical free and race-round condition implementation is the master-slave. So it is, if you look at the circuit, we have two NAND gate, which is SL latch. We have two NAND gate, it is two SL latch, and we have the feedback here, which is from a Q with J and Q prime, the feedback here, Q prime with K. So it is the same previous circuit with more sophistication. So we have J and K, okay, and one will act as a master and the second one will act as a slave. The output from the master is a QM here and a QM prime, and this is a clock circuit. So we have the clock pulse goes to a 3-input NAND gate on the top and the bottom, and the clock pulse inverted for the slave. See, we have an inverter, so the slave will have an inverted clock pulse. So it is two cascaded SL flip-flops, one acting as a master and is acting as a slave. The symbol or the symbolic diagram is shown, clock diagram of JK flip-flop. The clock pulse is again here the input, the output Q and Q prime, and JK the inputs. So figure A represents a cascade of two SL flip-flop with feedback of the output of the second, which is called the slave, to the input of the first, which is called the master. Positive clock pulses are applied to the master, and these are inverted before being used to excite the slave. When the clock is 1, the master is enabled and the slave is disabled, and vice versa, and hence the race round difficulty is solved. So we don't have any race round with master slave, and this will make it really a flip-flop to start with, a very stable flip-flop. Now the timing diagram of this circuit, if we assume J and K certain values, and we look at the clock pulse, and we look at the positive edge, because this is the positive edge, at the positive edge, the QM will change from 0 to 1. At the negative edge, if J is 1 and K is 0, will change back, Q will change from 0 to 1. So QM will change on the positive edge, while QM will change at the negative edge based on the values of J and K. And depending on J and K from the table, so we can determine how much Q plus is going to be. Okay. So here, for instance, we start to do the first pulse. At the positive edge, we see that J is 1 and K is 0. So this is a set mode. So QM will change from 0 to 1. At the negative edge, we see J is still 1 and K is still 0. So we have Q will trigger, and Q, which is the output from the slave, will change state from 0 to 1. So it is a negative edge triggered. And as a whole, the flip-flop will be a negative edge trigger. So Q will be at 1, which because Q is the output from the slave. And then we check actually for the next clock pulse. For the next clock pulse, the output will hold value until the next clock pulse. At the positive edge, we find J is 0 and K is 1. So this is a reset mode. And QM will change from 1 to 0. Okay, while Q is still holding. At the negative edge, we see J is still 0 and K 1. So this is, we are in the reset mode. So Q will change state from 1 to 0 at the negative edge, and so on and so forth. So we check at every edge, and as a whole, the flip-flop, the master-slave flip-flop will be a negative edge triggered, and this is why we have the small circle at the clock pulse input to indicate that this is a negative edge triggered flip-flop. So the next circuit will show you an improvement to the JK flip-flop accomplished by adding a preset and a clear. Preset or PR and clear CR control signal. The preset input sets the flip-flop when the clock is 0, and clear input clears the flip-flop when the clock is 0. So when the clock is 0, it means that this would be asynchronous, independent on the clock. We see that the preset is 0, the output Q plus will be 1. If the preset is 1 and the clear is 0, the output will be 0. So the preset and the clear will act without the clock. Once the clock is 1, this will act as a normal JK flip-flop. I will never allow the application of preset and the clear to be both zeros. So the preset and the clear. So the preset, when it is 0, will set the flip-flop, and when the clear is 0, will reset the flip-flop, and I will never allow them both to be 0, 0, because this will give me an invalid input. So I must avoid 0, 0. When I don't use the preset and the clear, either I set them to 1, 1, which is plus 5 volt for TTL logic, or I keep them open circuited. Just I leave them unconnected. Okay, so the input JK flip-flop, and this is, again, it is a negative edge triggered flip-flop with 2 output Q and Q prime. So this is a great improvement, which is the normal JK flip-flop as a module, as an integrated circuit, often has a preset and a clear. We will talk about this in next lecture. This is the last slide of the presentation. I would like to thank you so much for listening. Please subscribe and give me a thumb up. To subscribe, you need to click on the blue circle, which is the logo, and sincerely, hopefully to see you very soon. Sincerely, Dr. Hassan.